So hello guys. So in this video, uh, I'm going to share with you on how to prepare the impedance diagram and also how to calculate or determine the per unit impedances of its component. Actually, this is one of my project now because I'm going to prepare the fault calculations. So uh, the first part of this video is to prepare the impedance diagram and also to calculate the per unit value of each impedance, and in the next video let's do the calculations of the fault current at this bus and also at this bus. So in this diagram I only show you the rotating machines or the motor loads only, because these are only the loads that can contribute to the fault current. Okay, now here we have four numbers of submains, and it consists of the lump sum motors. So in here the first submain it consists of the total lump sum is, or the lump sum is 9.86 kVA, and we have also 26.28 kVA, 19.71 kVA, and 39.42 kVA. So the main feeder is two numbers of 3 core 100 mm squared, and also the sub feeders is 2 by 125 mm squared, and the length is estimated to 25 meters, and also here the length is 75 meters for the main feeder. Okay, so how to prepare the impedance diagram? So step 1, prepare the impedance diagram. Okay, so in this sample power system, first we'll prepare the impedance diagram. Okay, so first let's start from the impedance diagram of the generator. So generator is actually, we have the impedance diagram. The generator is, let's say this is say G. Next is the main feeder. Let's say this is said C1, and then next, since we have a bus here, so this just make so this is the bus. Okay, this is bus 1. Let's say this is bus 1. So you have four numbers of outgoing. So okay, and also the bus of the submain. This is the sub feeders of each submain, and you have the bus of each submain. Okay, then next, first we have to put some taggings in here. Since this is ZC1, so this is ZC2, C3, and this is C4 and C5. Okay, then connected to the bus are the lump sum motors. So let's say the impedance of the lump sum motors, this is ZM1 and also M2, ZM3 and ZM4. Okay, so now and also have to put the voltage source here. Okay, the voltage source, then so we have now the impedance diagram of this sample power system. So we have the G, or the impedance of the generator, impedance of the main feeder, and the impedances of the sub feeders, and also the impedances of each lump sum motors. Okay, now step 2, we are going to determine the value of each impedance. Okay, so in step 2, we are going to calculate the impedances from generator up to the motors. So it includes the cables also, and the motors. Okay, so here in step 2, let's start with the Z for the generator. For generator, ZG. Okay, now assuming that the generator is a salient pole with amortisseur windings. So from IEEE, standard 141, so for 12 poles or less than 12 poles, the subtransient reactance is ranging from 10% to 25%. So this is the subtransient reactance. Okay, now by using the mean value, the mean value is you have to add this 10 and 25, then divide by 2, so it is estimated at around 18%, the subtransient reactance. Okay, so we are going to use the 18%. Then for the since this value is based on the rating of the equipment, or the generator. So the formula for the impedance of Z impedance is equal to the subtransient reactance in percent divided by 100 times multiply by the S base over the SO, or the old impedance, old rating, or the rating of the genset. So it is assumed that the base power is 10 MVA and the base voltage is 220 volts, or 0.22 kV. So this is our assumption. So now let's substitute 18 divided by 100 multiplied by the base. The base power is 10 MVA over the old, or the MVA rating of the generator is 0.159 MVA. So therefore ZZ is equal to, using our calculator, so we have a value of okay, sorry, here J 11.32 per unit. Okay, so this is the impedance ZG for the generator. So next, for the feeder, main feeder, ZC1. Okay, the size of the cables is two sets of 3 core by 100 mm squared, and the length is 75 meters. Okay, now so I have here from table of IEEE standard. So for the 100 so I think it's very hard to, for the 100 mm, let's say 3 core and installed in a non-magnetic conduit, the resistance is 0.0614 ohms per 1000 feet, or 304.9 meters, and the reactance is 0.0283 ohms per 304.9 meters. So this is from the IEEE 141 table. So for 100 mm squared cable, the R, or the resistance, is equal to 0.0614 ohms per 304.9 meters. And for the reactance for this 3 core 100 mm squared is 0.0283 ohms per 304.9 meters. Okay, so these are the values taken from the IEEE tables. Again, so we are going to determine the impedance of these cables by applying the assumed MVA base and also the voltage base. Okay, so first for the the formula, the per unit, or let's say this is RC1. Formula is the R multiplied by the length over the N, or the set or number of set of cables, then the base power over the base voltage squared. Okay, so this is the formula. So therefore RC1 is equal to 0.0614 divided by 304.9 multiplied by the the length is 75 meters. This is 75 over divided by N. N is 2, so because this is 2 sets, so this is 2. Then the MVA base is 10, and the base voltage is 0.22 kV, 0.22 kV squared. So we have now RC1 we have now RC1 is equal to 1.56 per unit. Okay, next is for the XC1. So the formula is X times L over N multiplied by the MVA base over the voltage squared. Okay, so substituting XC1 is equal to 0.0283 over 304.9 multiplied by 75 meters over 2, then 10 over 0.22 squared. So this will become, so we have say J 0.719 per unit. So therefore the ZC1 is equal to 1.56 plus the reactance J 0.719 per unit. So this is the ZC1. And for the sub feeders, so they are also the procedure and how to determine is to do the same procedure. So for the next is we are going to determine the impedance of the lump sum motors. Okay, so since the procedure for the main feeder impedance calculations is also the same in sub feeders, so let's proceed to the lump sum motors impedances. And still we are going to use only one, and the other motors, the procedure is the same. Okay, now for the motors, for the group of motors as per IEEE standard 141, for the motors of less than 12. So here we are going to use the ZM1 or the first motors, which is around the lump sum is 9.86 kVA. Okay, so for the from IEEE standard, for the motors with 50 horsepower and below, less than 50 horsepower, the subtransient reactance is assumed to be 0.25. Okay, this is the assumed subtransient reactance value, and this is on the base is based on the rating or the lump sum of the motors. So now we are going to change this into a new per unit value, which is the ZM1, because we are using the S base, which is equal to 10 MVA. Okay, so ZM1 formula is equal to the multiply by the ZB over ZO. Okay, whereas SB is the assumed 10 MVA, and the SO is the rating of the equipment or the rating of the motors, which is 9.86 kVA or 0.0986 MVA. Correct me if I'm wrong. I think this is 1, 2, I think this is 2 zeros. 0.00986 MVA. It's 9.86 divided by 1000. Okay, it's correct. So 0.00986 MVA. So substituting these values, we have 0.25, 10 over 0.00986 equals 0.25 divided by 0.25 times 10 divided by 0.00986. So you have J 253.55 per unit. So these are now the procedure on how to determine the impedance value in per unit of the motors. So take note again, from IEEE, we use the value, the subtransient reactance, which is 0.25 because the motors is less than 50 horsepower. Okay, so we have now completed on how to determine the per unit values, or the impedance in per unit value. And in the next video we are going to calculate the fault current at this bus, the 3-phase fault current, and also the 3-phase fault current at this bus. Okay, so that's all for this video. Thank you for watching, and God bless.